Okay, students, welcome to section 2.5b continued. I'm going to be answering questions that I asked you to do for homework via the notes packet. We'll begin with the solving equation problem where 3x cubed minus 12x squared minus 5x, which I've already turned into plus and negative 5x, plus 20 equals 0. I've also told you that we're going to do this by factoring by grouping. So let's go ahead and continue. First step, after of course you've grouped it accordingly, is that we're going to go ahead and factor out the GCF. And in this case, 3x squared is the GCF. We factor out the GCF of 3x squared, we're left with x, and then we're left with minus 4. If you're ever curious as to whether or not you factored it correctly, distribute 3x squared, and you'll see 3x cubed minus 12x squared. The second binomial, we'll go ahead and factor out the GCF, in this case negative 5. And now with that GCF factored out, you'll be left with x minus 4. Now you do want these two binomials to be identical when you go through this process, and they are, which is fantastic. So what we do then is we take the x minus 4 GCF that's common between the two terms we see, factor out that, and we're left then with 3x squared minus 5. And then from here, because we're asked to solve, don't forget we want to set this equal to 0, which leads to x equals 4. We want to set this equal to 0, which leads to the following: 3x squared equals 5, x squared equals 5/3, and then that leads to x equals plus or minus, of course when square rooting both sides, x equals plus or minus root 5 over root 3, which I'll do a quick simplification of sorts, of course, which leads to this. So when it comes down to then my final answers, and there are 3 final answers, our final answers end up being x equals 4, and then plus or minus root 15 over 3. Moving on. On the next page, the next question that I had asked you guys to do for homework. So I asked you to solve square root of x plus square root of x minus 20 equals 10. The hint that I provided was to move the square root on either side. Whichever square root you want to move to the other side doesn't matter. I'm going to go ahead and move the square root of x as such, so minus square root of x, and I'll leave the square root of x minus 20 isolated as you see. So in the next step, we'll have the square root of x minus 20, and we'll have 10 minus the square root of x. When we go ahead and on the next step here, square both sides, we'll be left with x minus 20. You got to be careful here. You do have to FOIL. So 10 minus root x times 10 minus root x first. Outside, inside, so negative 10 root x and negative 10 root x adds to negative 20 root x. And then last, that'll just be positive x. So we see here now, as it turns out, we've got some terms that subtract out from both sides. And then I'm going to go ahead and subtract 100. The reason being, I want to still isolate, because I have a square root still sitting here, I want to isolate that square root. So this is what our next step looks like after you subtract 100. And then I'll go ahead and divide both sides by negative 20, which then leads to the following. We'll have the square root, and that will be equal to, as you can see, again, square root of x, and that will be equal to 6. To solve for x, we'll simply square both sides, and that then leads to 36 is x, or x equals 36. Now we still want to check our answer. Anytime we deal with a square root equation problem, we want to check our work. Instead of graphing this time, I will go ahead and plug in 36 for x. And our quick check will look something like this. So we'll say square root of 36 plus square root of 36 minus 20. Does that equal 10? Well, the square root of 36 is 6. 36 minus 20 is 16, the square root of which is 4. So yes, 10 does in fact equal 10. So my answer of x equals 36 is correct. The next question that I had you guys do on your own for homework, partly was the second question of the polynomial inequality variety. We did begin the question in class, number 2 that is, in which we set up for, by subtracting 5x and adding 10 to both sides, we set up for setting our inequality as such, greater than or equal to 0. Now, according to the boundary algorithm, we're going to make 2 side notes. Number 1, the fact that it's greater than or equal to 0, we say that it's positive. At least we want values that are positive outputs when we plug in values on our number line. We also want closed critical values. So we make our number line, they'll be closed at those particular values. So I went ahead, if you guys recall, in class, I did factor out the GCF of 3x squared. Okay, I did have to check that. And then, of course, you're left with x minus 2. If you want to double check, though, 3x squared times x is 3x cubed. 3x squared times negative 2 is negative 6x squared. Noticing again, I did change my sign to, instead of minus, turned it into a plus and negative 5x. When I did my factoring by grouping, I did put parentheses around the negative sign, which is imperative because in the next step, when I factor out my negative 5, you are going to have then the same binomial as you see back here. So x minus 2 and x minus 2. It's still set equal to 0. We always want to do that so that when we find our critical values, it's very obvious what we're talking about and how those values will be represented. I went ahead and factored appropriately where x minus 2, that was the GCF between those 2 major terms in the previous step, and I'm left with 3x squared minus 5. Set x minus 2 equal to 0, got 2. Set 3x squared minus 5 equal to 0, and I got, add 5 divided by 3, got this, which we then can simplify as such, plus or minus root 15 over 3. And I got that again by multiplying numerator and denominator by root 3. So on our number line, we'll go ahead and take a look. Our number line will have 3 critical values, of which we'll go ahead and identify negative root 15 thirds, positive root 15 thirds, which if we do a quick analysis gives us root 15 over 3 as 1.29. And then, of course, negative root 15 over 3 is negative 1.29. So I'll kind of note those as such. Okay, and I will be able to then put 2 somewhere here, which I think I can do easily enough. Or not. Let's do this. So let's say 2 is here. Again, if you recall, we wanted closed values at the 3 critical values, so I'll do that. And we'll go through and test intervals. Okay, so when it comes to testing intervals, what you're going to go ahead and do is you're going to type in on your calculator a number that is less than negative 1.29, between negative 1.29 and positive 1.29, and then, well, in between these two, and then really the fourth and final interval will be greater than 2. So we'll go ahead and do that. Let's go ahead and type in a number like, gosh, negative 2. So we type negative 2, store as x, and then we type in the original problem, which again was with the inequality set so that it was greater than or equal to 0. We'll say then 3x cubed minus 6x squared minus 5x, or plus and negative, which is still okay, plus 10. Just simply type that in. Keep in mind, your goal here, once I hit enter, your goal here is to get a positive value. Because we didn't get a positive value, we're going to say that any number to the left of the first critical value is not a solution. So we won't worry or concern ourselves with that. You could do the same with 0 on your graphing calculator, although you could easily just plug it in here. So 0, 0, 0, that all turns out to be 0. Then you have 10 is greater than or equal to 0, which we know is true. 10 is greater than or equal to 0. There we have our first interval graph. Between 1.29 and 2, we can pick a value like 1.5, which is not too bad. Storing again as x. And then we'll hit second enter. second enter. When you hit second enter twice, boom, there's your function again. Hit enter. There's another negative. All right, we don't want that as a solution. And last but not least, we'll test a number like 3, a number bigger than 2. Pick 3. And I'll do that on the calculator. 3 stores x. Second enter. Second enter. And then 22. That number is positive, which is what we wanted. And that then leads to our final graphical depiction of what the solution is. When it comes to then identifying our final answer, interval notation-wise, it will look something like this. So negative root 15 over 3, comma root 15 over 3. And those both have brackets, because we know that they're closed there. And that's in union with bracket at 2 to infinity. And that's obviously finished off with the parentheses. What I wanted to finish up with here today is taking a look at the other worksheet that was handed out today, and that's the solving inequalities, technically solving polynomial inequalities page that I've created on OneNote. I'm going to walk you guys through generically here how to do the same type of problem, but instead of using the boundary algorithm, we'll use a sign chart or sign analysis. Objectives: solve polynomial inequalities algebraically using a sign chart. Second, solve polynomial inequalities using a graph. So for solving polynomial inequalities, we're going to do this such that they hinge on finding the zeros. The zeros are called critical numbers, or critical values is what our textbook defines it as, or has in the past. These numbers separate the number line into intervals, and then the sign chart is used to determine the intervals in which the polynomial is either positive or negative. For example, solve x squared plus 2x minus 3 greater than or equal to 0. So first, you're going to factor to find the zeros as you see x plus 3x minus 1, which is the factorization of this quadratic. You still set it greater than or equal to 0. And in turn, x equals negative 3, x equals 1. Now what they have not done is made the note that we are going to have closed circles at those particular values, but that may already be obvious based upon the fact that it's greater than or equal to. So I'll go ahead and plot those for us. And we think about on the interval left of negative 3, in between negative 3 and 1, and greater than 1, what are we going to get as outputs? Just like we saw with the boundary algorithm. It says arbitrarily choose a value in each interval and determine whether it's positive or it's negative. Again, we still need to make the connection that we want positive values. So all these things are still critical in our understanding and our analysis. So what we'll go ahead and do is pick values that are less than negative 3 arbitrarily. I'll pick negative 4. Values between negative 3 and 1, I'll pick 0. And then values to the right of 1 or greater than 1, I'll pick 2. What I'm going to then do is I'm going to make a little table, and it's a little bit different in the setup of solving this particular problem, where x plus 3, one factor, x minus 1, another factor, and then I'll write the intervals, generally speaking, negative infinity to negative 3. Also, negative 3 to 1. And then lastly, we'll have 1 to infinity. And then simply, if we plug in negative 4 here for x, negative 4 plus 3, of course, is negative 1, so that's a negative. Plug in negative 4 here, negative 4 minus 1 is negative 5, so negative. We'll continue the process, but now with 0, plugged in becomes positive, plugged in here becomes negative. And then similarly with 2, we plug in 2 plus 3, 5, so positive, 2 minus 1, 1, so positive. The result of multiplying these two factors' signs, so this will become positive, this will become negative, and this will become positive. So when we wrap this up, we can see positive, negative, positive, and because we wanted positive results, we only include those, so left of negative 3 including it, and right of 1 including that. Keep in mind as a final little note, our inequality stayed as is, just as a reminder, but when we did the boundary algorithm, we actually changed it into an equal sign. I think it's pretty intuitive still, though, that those critical values are in fact negative 3 and 1 with or without the inequality.